Thank you, Chair. Good afternoon, everyone. So I'm application scientist from Horiba Scientific. Today I'm talking about the influence of numerical aperture on micro-reflectance spectroscopy. So for reflectance, it's defined as the fraction of power in the instant wave that is reflected. So in this case, beside the reflection spectrum from the sample, we also need the spectrum from the reference spectrum, so which can be the reflection signal from a mirror, for instance. So the appropriate mirror is capable to reflect instant light almost completely, since our test is on visible range. And so we choose the aluminum mirror according to this chart. So we noticed that the objectives with different numerical aperture actually has different performance during our experiment, especially on scattering sample. So in this talk, we're going to discuss the difference between the two samples and numerically compare the reflectance by calculating the micro-reflectance difference on the two samples. So here shows the micro-reflectance measurement. On the left is on the shining surface. So the reflectance mainly comes from the specular reflection. So here shows on the rough surface, which is different because both specular and the diffuse reflection represent. So we need to consider both parts. So in this case, we need to introduce other techniques such as the detector mounted on the gynometer or the integrating sphere to collecting scattered reflection. So in micro-reflectance measurement, both specular and diffuse reflection also need to be considered. So here on the right side, we show the white light spot size focused by the 10x objective on the sample surface. So the top one shows the spots, the white light spots focused on the specular substrate, so which is visible because it has very shining reflection. But on the bottom one, the spot is focused on the scattered surface. So because the reflection, it has very strong scattering, so we can barely see the spot size. So the numerical aperture of the objective plays very important role on the scattered surface because the divergence angle here determine the range of angles can be collected. So we expected that the larger numerical aperture can collect more diffused reflection from the scattered sample surface. So in this experiment, we use our standard microscope spectrometer to do the experiment. So the left one shows our schematic setup. So we use the halogen-like source, which is from 400 nanometer to 1000 nanometer. It's coupled by a multi-mode fiber. The core size is around 10 micron. So the instant light is coupled by fiber and focused on our very powerful motorized stage, which is built on our standard microscope platform. So the motorized stage is we use it to determine the interesting area and also do very fine structure mapping. So the emission was collected by the periscope and go to our collimated into our spectrometer and further detected by CCD, and all our data analysis by our software LabSpec. So here shows our front view of our setup. So here shows the spot size on different samples. So the top is the on silicon sample under different objective from 10x to 100x respectively. So the resolution of the spot size can be as small as 1 micron, and the bottom one shows the sample and the white spots on the scattered sample surface, which is the molybdenum disulfide (MOS2). So this is the MOS2 flake on the glass substrate. So we can see that on the glass substrate, we can see the spots very clearly. So on the 100x, so here is our spots, which is very tiny. So in order to numerically calculate the spot size, we measure the beam profile by calculating the full width of half maximum to the Gaussian distribution. We can see that for the 10x objective, the beam width is around 5 micron, and when the objective is larger than 60x, the beam width can be as small as 1 micron. Okay, so here gives an example of our raw data. So we do measure the reflection from the mirror, aluminum mirror, at a visible range. So the red one give us the mirror spectrum, and the blue one is a signal from the silicon sample surface. And here are the background. We do the subtraction of the background from the sample spectrum to get the corrected spectrum, and do the ratio to get our reflectance. So here is the reflectance spectrum on the silicon wafer. So we can see that the reflection is almost completed, collected by our objective, so which is much higher than the macro reflectance measurement. So this is the reflectance measured on the silicon solar panel. So we can see that on the micro reflectance is much higher than the macro measurement. And then, however, the different numerical aperture of the objective doesn't have very different performance on silicon sample surface. So which is expected because it's a specular sample surface. We expect that all the reflection can be collected by our objective. So here gives us the MOS2 flake. So we can see that the reflectance is much smaller than silicon sample, and also the reflectance is follow the sequence of the numerical aperture of our objective. So with the larger numerical aperture, for example, here is the 100x and 60x, 40x until 10x. So it follows the sequence of the numerical aperture. So this is expected because the larger objective numerical aperture showing an increased ability to collect diffuse reflection because of larger divergence angle. So we compare the micro reflection difference between the two samples. So on silicon sample surface, so the micro reflection difference ideally to be 0. So here is around 4. It's accepted because it's under the uncertainty of experimental condition. So but on the scatter surface, here is the MOS2 flake. The micro reflection difference is around 30 times larger than silicon sample surface, and we can see that the reflectance is increasing while the numerical aperture is increased. So in addition, I also want to show that our SMS system also has very good performance on the reflectance mapping function. So on the left side is on the silicon sample with gold etching on the surface. So the top one is 60x. The resolution is 1 micron, and the bottom one is 10x. On the 10x objective, the resolution is around 5 micron. And then the left one is our MOS2 sample surface on the glass substrate. So we can tell that the reflectance on the sample surface is much smaller than the substrate. This is on the 20x objective. So in conclusion, our SMS system shows a very good performance on the reflectance measurement. And so this is our classic system based on the standard microscope, which accommodates for almost major spectroscopy such as Raman, PL, lifetime reflectance, for example. So we investigate the influence of numerical aperture of the objective on different samples. So we noticed that on the specular surface, such as silicon wafer, the reflectance shows much has higher efficiency on reflectance than the macro measurement. And on the scattered sample surface, such as MOS2 flake, the micro reflectance measurement actually has strongly depend on the numerical aperture of the objective. So in order to get a more accuracy of the reflectance, we have the preference to choose higher numerical aperture of the objective. So thank you for your attention.